Have you ever wanted to know what lies at the heart of an exoplanet? Of course you have. Who wouldn't? What if I told you we can now answer this question? Not for just any planet, but for Kepler-452b, one of the most distant planets known to man. We know some things about this planet. It orbits a star 1,400 light-years away from Earth in the constellation of Lyra. It's 60% larger than Earth and has a mass about 2.5 times greater. And the star it orbits is similar to our Sun. This means that the planet could have liquid water on its surface, which is why scientists became so interested in studying it. But how did we manage to find out what this distant planet is made of? If we know its density, then we can find out what the planet's made of. To do this, we need to measure its radius and mass. The radius we can get from the transit method, which Kepler was designed to do. This method consists in measuring how much the brightness of a star decreases when a planet passes between us and the star. If we know the brightness of the star and how much it decreased, we can calculate the size of the planet, because the decrease in brightness depends on the area of the planet. This method is quite simple to explain, but it took astronomers years to perfect. The mass of the planet can be measured with the radial velocity method, which again Kepler was designed for. This method is based on the fact that when a planet moves around its star, it pulls on the star with a force, and the star moves too. In other words, they move around a common center of mass. The planet will be closer to the center of the system, but the star will also shift towards the planet a bit. As a result, the spectrum of the starlight will shift towards the red part, which corresponds to an increase in wavelength. When the planet is farther away, the spectrum will shift back towards the blue part. These shifts can be very accurately measured with the radial velocity method, which in turn allows you to calculate the mass of the planet. So the mass and radius are known, which means we can calculate the density. But the problem is that the mass and radius we got are just some values within a certain range, not exact values. Indeed, there can be many combinations of radius and mass that fit the observations equally well. So which combination should we choose? Which radius and mass values should we use to calculate the density? In order to solve this problem, we need additional observations. For example, observations of artificial satellites that pass near the planet. But even this is not enough. We also need theoretical calculations, and here come the physicists. They used computer simulations to calculate how fast artificial satellites would decay in orbit around such a planet. The thing is that if a planet has a strong gravity and a dense atmosphere, then satellites will quickly decay into the atmosphere and won't be able to stay in orbit. On the contrary, if the planet doesn't have much gravity, then satellites will easily remain in orbit. The researchers assumed that the observed range of values of the planet's mass and radius corresponded to the minimum and maximum possible values. All the values between these limits were physically possible. And then, they calculated how well these values fit the observations of artificial satellites of the planet. As it turned out, the combination of mass and radius that best fit the observations was the one that gave the lowest density. But what does this mean? It means that the planet's structure must be such that its density is minimal. And what kind of planet can have the minimum density? That's right, a huge ball of cotton candy. No, more seriously, a planet made mostly of hydrogen and helium. However, this is unlikely because such a planet would have had a strong gravity. And observations show that this is not the case. Most likely the planet has a rocky core, something like Earth, but it must be surrounded by a layer of insulating material, something like ice. And the higher the layer of ice, the lower the density. So the researchers concluded that Kepler-452b most likely has a core like Earth, but it is much larger and covered with a thick layer of ice. This model fits all the available observations. First, it explains why the planet is so large and massive. Second, it explains why the planet has such weak gravity. And third, it explains why we haven't seen any atmosphere on the planet. Well, it's explained why we haven't seen any atmosphere because there isn't one. The ice layer prevents the gas from escaping into space. But how thick is this icy mantle? According to the researchers, its thickness is at least 37 kilometers, And since we know the volume of the planet, we can estimate how much water is contained in this layer. As it turned out, it's about 23 trillion cubic kilometers. For comparison, all the water on Earth fits in 7.1 trillion cubic kilometers. So the amount of water on this planet is 3 times greater than on Earth. Moreover, it's not excluded that the planet's mantle goes deeper, and the ice layer is as much as 100 kilometers thick. In this case, the amount of water will be already 60 trillion cubic kilometers. And if we assume that the entire mantle is made of ice, we can estimate its total thickness. It'll be about 250 kilometers. This value agrees well with the modern ideas about the structure of the planet. In the layers deeper than the ice mantle, the pressure will be so great that the ice will turn into a form of ice that conducts electricity and even supports life. It's called superionic ice. And what will happen to the water molecules? Their oxygen will bind with the iron in the planet's core to form rust. And this rust will make the planet's core conductive, which in turn will lead to the emergence of a magnetic field. Scientists believe that without this process, there would be no magnetic field. But the presence of a magnetic field indicates that the core is liquid, while computer simulations suggest otherwise. It turns out that the only way to explain the planet's magnetic field is to assume that it has a liquid core. So either the planet's core is liquid, or it's covered with a 250-kilometer thick layer of ice. And although the first option seems more preferable, we cannot completely rule out the second one. This means we still don't know what's inside this planet. However, it is equally likely that the planet's composition is like that of Neptune, a small rocky core surrounded by a thick mantle of ice and a gaseous envelope, and therefore its mass may be less than that. The measurements of the mass and radius of the planet were quite accurate, but we still have a lot of work ahead of us to determine what exactly this exoplanet is made of. There's one important detail. The results of this study hold true for all exoplanets of the super-Earth class, that is, planets that are slightly larger than Earth. There are thousands of such planets in the Milky Way, and perhaps some of them have conditions suitable for life. It's entirely possible that somewhere out there, thanks to this study, scientists have brought us a step closer to finding another Earth. Of course, you want to know more about exoplanets, and we have a whole playlist with videos about them. There, you'll find answers to such questions as, can you see an exoplanet with your own eyes? Can you hear music on an exoplanet? How do exoplanets form? And what's the strangest exoplanet ever found? You'll find all this and much more in our new videos.